All right, people, let's take a look at ownership in Rust. And what is ownership in Rust to the Rust developers themselves, the creators of Rust? As they say, ownership is Rust's most
unique feature
and has
deep implications
for the rest of the language. And it kind of does. You guys are going to find out about that in a little bit. Essentially, ownership is what enables Rust to make these memory safe guarantees without needing a garbage collector. If you don't know what a garbage collector is, let's take a look at that really quick first. All right, so what is a garbage collector? And as you guys can see from this nice little picture right here, this is our garbage collector. Looks like you are not using some data. Let me free it for you. Here's what the application memory is going to look like. You got some used data in the green squares and some unused data in the blue squares. Here's your RAM thanking the garbage collector because it's like, oh, super cool. My memory is back. Wow. And there's the developer. This is amazing. I didn't need to use free anymore. If you guys couldn't get the joke, basically garbage collector is just something that if you're a developer, you really don't have to think about. You don't have to think about all the different variables and data structures that you've used or created. You don't need to think about what's going on in the background with them with your actual computer because the garbage collector is basically automatically taking care of the memory management from your software that you wrote. And it's doing it for you, right? That's automatic. Things used to not be like that back in the good old days. But more importantly, back to Rust. So what is this ownership thing? Ownership is just kind of like a set of rules that kind of dictates how the Rust program or a Rust program is going to manage memory. And keep in mind, we just looked at what a garbage collector is. All programs have to manage the way they use a computer's memory when the program is running. Some languages, a lot of modern languages have a garbage collector, kind of does all this stuff for you. And in other languages like Rust, C, C++, you as the programmer, you must explicitly allocate and free up the memory. However, the unique thing about Rust itself that kind of makes it a little bit better and different is that Rust uses this kind of like different approach where memory is managed through a system of ownership. And ownership is just kind of like a set of rules. And when you compile your program, the compiler is going to check to make sure those rules are being adhered to. And of course, if the rules are not being adhered to, then the program's just simply not going to compile. And this ownership thing, it's not like a kind of common thing used by most programmers, so it might be a little bit weird at first, but if you do it long enough, it just becomes kind of like second nature, just like everything else that programming does as well. And in order to really be able to utilize Rust for what it's good for, you got to have to understand ownership, because without ownership, you're never going to be able to utilize all the features that make Rust truly unique. There's this thing called the stack and the heap, and most programming languages don't require you to like even think about the stack and the heap very often. And by the way, guys, if you don't know what the stack and the heap is, I don't want to go super deep into it in this video because it's going to take way too long. You can just think of the stack and the heap as kind of like little areas of your computer for memory, in memory for your program that is running. Most programming languages, you don't have to even think about the stack or the heap when you're writing your code, but in a systems programming language like Rust, whether or not a value is on the stack or the heap, that's going to affect how the language is actually going to behave and why you're going to have to make certain decisions with your programming when you're actually doing your development. Just wanted to note that for you guys going forward. More deep into the actual ownership thing in Rust itself, there are 3 rules for ownership in Rust. So let's take a look at those. So the first of these 3 rules for ownership in Rust is that each value in Rust has this thing called an owner. And yes, I'm going to explain what an owner is. Second rule is that there can only be one owner at a time. And the third rule is that when the owner goes out of scope, the value is going to be dropped. And I suppose for simplicity's sake, I'll just go ahead and give a quick explanation of scope, although you probably already know that, or you should already know that if you're on this video. All right, so I'm just going to make another little section inside of the main function just with curly braces, and we'll make this little variable called s. We'll shove it inside of there, and here's some comments, okay? And by the way, s, we're going to be setting it equal to hello. So at this point right here on line 9 where the curly brace begins, and keep in mind this section is inside of the main function, so you can think of it as this section is inside of another section, which is this section up here. At this point on line 9, s is not valid, and that's because it's not yet declared. Line 10, we make the variable s is valid from this point forward. After that, you can do stuff with s, and then at this point, line 13, the end of this curly brace scope right here, the scope is now over, and s is no longer quote-unquote valid. That probably wasn't the best explanation of scope. Go back and check another video in this tutorial or in another tutorial, and you know what? I'll just do a video of scope in general in Rust, although I'm pretty sure I've already covered that in somewhere. But nonetheless, the 2 things I want you guys to take away from this example or this explanation is that when s comes into scope, it's quote-unquote valid. And then that it remains quote unquote valid until it goes out of scope. And this is pretty similar in other programming languages, okay? All right, so now let's talk about memory and allocation. So you guys are familiar with a string data type in Rust, and I've just used it several times in this video. And that specific string type, by the way, guys, is called a string literal. And we're not going to use that for this example because when you create a string literal in Rust, it automatically is going to be immutable. And trying to kind of explain ownership with an immutable string, I'm not going to be able to show you guys like that because string literals are convenient, but they're not really suitable for every single situation in which you might want to use text. One reason for that is because they're immutable. And another is that not every string value can be known when we write out our code. So for example, if I want to take a user input and store it, how do we know what length of the string the user is going to type in every single time? I mean, we don't, right? So for situations like these, Rust has a second string type, and that's just called string. So string is just different from string literal in that this quote unquote string type, it manages data allocated on the heap. Remember the heap in the stack that I talked about earlier? This manages data on the heap. And because of that, it's able to store an amount of text that is quote unquote unknown to us, like the example I just told you guys with the user input at compile time. And you can create this string type from a string literal using this thing called the from function. So let me make my string literal first. Let s equal string. So I want to actually type out the name string with a capital S, kind of like from the string class. Ooh, colon, because we need to call a function from it, right? And this function is called from, and I'm going to say hello. Boom, there you go. So this kind of acts like the dot operator, the colon. You guys know that already, but the double colon operator is going to allow us to use the namespace from this from function under the string type, as opposed to using some kind of name like string underscore from or whatever. But don't worry about that. This kind of string, guys, this kind of string can be mutated. And how does that work? Well, then I can just take s and I can say like s dot push underscore string, and then I'm just going to pass the string. I'll say comma space world. Oh, hello world. And then let's print it out with a print line macro. Oh yes. Yes. Forgot the mut keyword. I like to call it mut. So like what is the difference now between this string and like what we've been doing with a regular string literal? Why can this string type be mutated, but string literals can't? That's because the difference in how these two types are dealing with memory. So back into that memory and allocation explanation. When we have a string literal, the kind of strings that we've been using before this in these tutorials, not this one, we already know the contents of the string when we go to compile our Rust code. And that's because that text is like hard coded in there directly, which makes these string literals fast and efficient. But those properties of being fast and efficient only come from the string literal's immutability. So we can't just put like a blob of memory into the binary files for our compiled code for each piece of text whose size is unknown at compile time. And also like the size might change when the program is running, right? So just with the regular string type, in order to support a mutable and growable piece of text like we want to be able to do, we need to allocate an amount of memory on that thing called the heap again, which we're not going to know at compile time. And that is going to hold the contents of our string. So this pretty much means that memory must be requested from the memory allocator during runtime. All right, guys, that's important, during runtime. And we need to have some kind of way of returning this memory back to the memory allocator when we're done with that string or with this new string. And the first part, the whole memory must be required from the memory allocator at runtime. That part's done by us when we're calling this string colon from. This implementation requests the memory it needs. And this is kind of like the same in all programming languages. However, the second part where we need a way of returning the memory to the allocator when we're done, that part is different. So in languages with like a garbage collector, the garbage collector is going to keep track and clean up all that stuff and do it for you because you're all lazy. And I am too, so it's okay. But that's why we're here to learn Rust, right? So with Rust, it's our responsibility to identify when memory is no longer being used, and we need to call code to explicitly kind of quote unquote free it up. We need to release it because we all have very tiny computers with like a half gigabyte of memory, right? Wink, wink. And by the way, doing this the right way has kind of like historically been a quote unquote difficult programming problem. It's not fun or easy to do with things like C or C++. And if you forget, you can waste memory. If you do it too early, you can have like an invalid variable. If you do it twice, you can create bugs. So basically what we need to do is we need to pair exactly one allocate, every one free. And with Rust, it's a little bit different. Remember I told you guys, Rust a little bit different though. With Rust, the memory is automatically returned once the variable that owns it is going to go out of scope. And if you guys remember the little scope example I gave you guys earlier, this is basically the same kind of example, but we're using our new string type instead of our string literal. So at the beginning, once we get into scope right here on line 16, after that, line 17, we create this new S string variable and it's valid going forward, then we can do stuff with S inside of our scope. And then line 20, it's no longer valid. It's over. It's ogre. So with that being said, there's this kind of like natural point at which we can return the memory of our string to the allocator, whatever amount that it needs. And that is when S is going to go out of scope right here. When a variable goes out of scope, Rust calls a special function for us, and that's just called drop, D-R-O-P. You don't have to do that though. Rust is going to do it for you. It's going to hold your hand, all right? And that is where, when you created the string, the author of the code can put the code to return memory, or where you would put that. But Rust calls drop automatically at the closing curly brace. And Rust is going to tell you that because of this, and I don't mean to joke about it, like, because it's
super cool and amazing, and totally Rust is number one. Haha.
Rust developers are going to tell you that this pattern itself kind of has a profound impact on the way that Rust code is written. It really does. It really does. But I know it seems kind of simple, but the behavior of code can be unexpected in more complicated situations than like the little example that we're doing here. Like when we want to have multiple variables, use data that we've allocated on the heap, et cetera, right? And there's a lot of things to talk about with that as well. But you know what? I think I will save the ways that variables and data are going to interact for the next video. Hope that helped. Smash the like if you enjoyed the content, if it helped you out. Developerdirection.com to sign up to the email list and get a GitHub guide, make you a project or two. Leave a comment if you want me to clarify something else in a different video, or don't do any of the above. I'm out. See ya.